Hi everyone, my name is Anthony Bover, and for this video we are going to be looking at constructing a helical pipe. So we're going to be given these functions here that, based off of our parameter t, give us our x, y, and z coordinates. And what we want to do is construct a circle around a line that follows these coordinates. I think it'll be easiest if I just go ahead and draw it out. So I'm going to go ahead and do that. I'm going to first import numpy as np. Numpy will allow us, it gives us access to a library of functions that can help us make arrays, use sine, cosine, pi, stuff like that. And then I'm going to go ahead and enter these in. So x equals, we'll call it r times np cosine of t. Y equals r times np sine of t. Z equals, we'll call it mz times t. And then from there, what we'll say is r equals 3, which is given to us here, 3, and then mz equals 0.4. Okay, so shift enter, it's looking good. And now we're going to go ahead and graph this. So we're going to use Plotly. So I'm going to go ahead and import that. So Plotly, so from plotly.subplots, import make subplots, and we're going to create a figure here, make subplots, and figure dot add scatter. I think it's an underscore. Yeah, add scatter. And then we want it to be 3D. And then we need to give it our 3 variables. So for our x values, we'll use our x values from up here that we defined already. Y values equals y. And our z values will equal z. Run it. Okay, and we get a helix. I'm going to make this, I'm going to get rid of those dots, so mode equals lines. Run it again. Okay. Now, one thing I actually didn't specify was what our t value should be. So t equals, we're going to make an array of values for t to take on. So we'll use linspace. We want our values to go from 0 to, I don't know, let's say 10. And then we want to use, we'll say n. So this will give us 0 to 10, numbers 0 to 10, with n equal values in between those two. So we can set n to be 50. Run it, run it. So this should give us 0 to 10. Now, one thing to note about circles is that a full circle will be when t equals 2 pi. So if I would want to change this in terms of pi to speak the language of circles. I actually wanted to go around twice, so I'm going to do 4 pi. So this should give us a spiral that goes around twice. Okay, perfect. So now what we want to do is take any point on the circle, and we want to draw a circle around that point and the circle should be perpendicular to the curve. And we want to do that all along this line in order to make a pipe. So the way that we're going to do that, let's see if I can get a good view here. If we take a point on the circle, so let's say this point right here, um, and we take the tangent vector to that point, that tangent vector is going to point in a direction like this. If we were to take then the normal vector on that curve, the normal vector would point inward, so towards the center. Those two vectors will be at a right angle to each other. If we were to take the cross product of those two vectors, we would get a third vector that points directly up, directly toward the screen, directly towards me. Then we could take that vector and take the cross product with the tangent vector, and that would give us a plane that is perpendicular to the point on the circle. And using that plane, we can draw a circle around our point, and that circle can have a radius of 0.5. And if we do that for every point, then we will have a pipe. And that's exactly what we're looking for. So we need to find the tangent vectors for any point on the curve and the normal vector for any point on the curve. Now, one thing we know about circles is that if we know the equation for the circle, the velocity of the circle, the equation for the velocity will be the tangent vector to the circle. And if we take another derivative, the acceleration equation will be the normal vector. So if we're able to find the derivative and the second derivative of the equation for the circle, we will be able to get the tangent vector and the normal vector. So that is what we're going to do. So to start, I'm going to find the Jacobian of the curve, which is it's the partial derivative. It's a matrix of the partial derivatives. I'm going to first do it using closure, and then I'm going to do it using Jax's automatic differentiation. So one thing to note about the Jacobian is that it gives us an array of basically all partial derivatives for all functions. So looking at this matrix here, as we move along the rows, it gives us the partial derivative of the first function with respect to the first variable, the first function with respect to the second variable, third variable, fourth variable, so on. And then as we move down the columns, we will get the partial derivative of the second function with respect to the first variable, second function, second variable, second function, third, fourth, fifth, sixth, and so on. So what we end up with is a matrix of every partial derivative for every function. Now in our case here, I'm just going to go ahead and just make a function. So we'll call it f. And what we want it to do is return sine of x plus cosine of y. So in our case, we have one function. The Jacobian is for many functions. In the case of one function, we can actually use the gradient, which is the partial derivative. It's a matrix that gives us the partial derivative of the function with respect to the first variable, second variable, third variable. So in our case, it will be the partial derivative with respect to x, and then with respect to y. So the way I'm going to do this is this x that it takes in should be an array that contains the values for x and y. So I'm going to code this out by saying that this is going to be the first value in that x array, and this will be the second value in that x array. And then what we want to do is the gradient, we're trying to find the gradient, so we need the partial derivative with respect to the first variable and then the second variable. So I'm going to define a function called getGrad of, and then we'll take in a function f. Within this function, I'm going to define a function called gradient, which will give us the gradient at specified coordinates, so x. and then the derivative, it will give us the derivative. So the derivative is going to be, I'm going to use the definition of a derivative. So f of x plus h minus f of x divided by h. So this will give us the slope between 2 points on the curve, and that is the derivative. H should be a very small number, so the points are very, very close together. And then what we will do with that is we want to add it into, I'll make an empty array called res for result, and what we will do is add that value in. Res.append, that's not right, res, derivative. So what res will end up being is an array that has all of our derivatives. So the derivative with respect to x and then with respect to y. And then this should return an array. It should make res an array and return it. And then gradient, and then our get gradient function should return grad. Okay, run that, looks good to go. Now we need to specify what values we want for x and y. So I'm going to call this x naught, and I'm going to set it to be pi for both. Okay, that was weird. So pi and pi, so we're going to get the gradient when x equals pi and y equals pi. And we actually need to make this an array. And then what we want to do is say f gradient equals get gradient for f, and then we want to do f gradient at x naught. Okay, error, h is not defined, so yes, we add h here, we divide by h here. We need to specify what h is, so the way I'm going to do that is add it here, and we will call the function using that h value. It should be a very small number, so I'm going to do 1 times 10 to the negative 10th. Shift enter. So what we end up with is a value -1. Okay, so this should be the partial derivative with respect to x. So if we look up here back at our function, sine of x plus cosine of y, if we were to take the partial derivative with respect to x, that would give us cosine of x plus 0. The cosine of pi, which we specified down here, is -1. So this is correct. -1 is correct. And then what we need is the partial derivative with respect to y. So if we were to do that, it would be 0 minus sine of pi, which would give us 0. So what we want is an array that contains -1, 0. And the reason why there's only one number here is because we're only doing this once. So what I'm going to do down here is say for I in range, and then we want to, however big x is, that's how many times we want to do this, because it needs to be for every variable. So this will be x dot size, and in this case it will be 2. There's only 2. There's x and y in there. Okay, run that. Now we have 2 numbers here, but this one is not correct. This should be 0, not -1. And I think the way we want to handle this is we want to create a new array called x plus h. x, we'll just x plus h, and we want to copy x over. So we'll make a copy of x, and then for every I value, what we want to say is x plus h, the value in that array at I for x plus h equals the value for x. And then we're just going to add h directly to it. And then down here, x plus h, we can just say x plus h. And then after doing the derivative, we can return that to where it was before. So x plus h I equals x I. Run it, run it. Okay, and this is what we were looking for. We get -1 and we get 0. That's exactly what we're looking for. So this is the gradient for our function. So that was done using closure. And I guess I want to speak a little bit about this down here. The reason why we can say f grad equals get grad f, and then call this grad from f grad, is because when we run this line, this makes f grad basically take on this function grad, and the function kind of goes inside f grad, which allows us to call the function from f grad, and that's why this works. So now what I'm going to do is use JAX to do automatic differentiation. So we're going to use jax.grad, and what JAX is it's a library of functions, kind of like NumPy, and you'll see in a moment that there's a lot of similarities to NumPy. So what we're going to have to do is import JAX and import jax.numpy. I'm going to call this JNP, which will make this a bit easier to use. And then what I'm going to say is f, what do I call this? We'll call this the JAX gradient equals, I believe it's, yeah, jax.grad. Jax.grad of f. And then we want to do jax j grad at x naught to get for those same points again. And it'll throw me a few errors. Well, actually, I should go ahead and run this. The reason why I'm getting errors here is because JAX kind of contains its own functions that it would prefer us to use rather than our NumPy functions. So I'm just going to do this all down here to make it a little bit easier to understand. So I'm going to copy this down. So define f JAX, we're going to call this f JAX, and it will return, instead of doing np.sign, we're going to do jnp.sign, jnp.cosine. And then we want to copy this down too. Copy, paste. Instead of x naught, we'll call it xj for our JAX values. jnp.array, jnp.pi, jnp.pi. So f JAX and xj. Okay, and we run this, and JAX tells us that our gradient is -1, comma, basically 0. 8 times 10 to the -8 is basically 0. So comparing these two, we have -1, comma 0, -1, comma 0. So using both closure and automatic differentiation with JAX, it gives us the same answer. And this is what we want to do with part 1. One thing I will do is use the Jacobian, use JAX, use the Jacobian, that's part of JAX. Um, so I'll say J underscore Jack equals Jack's dot Jacobian of f Jacks. And then I want the J dot Jacobian at the point xj. And what it gives us is -1, comma 0 again. And I was just showing this to, I guess, clarify that the gradient and the Jacobian are the same because we only have one function. So this is part 1, and I will be doing part 2 in the next video. Thanks for watching.